Welcome students. In this lecture, we are going to discuss some examples related to central limit theorem and estimation problems. The theory related to these topics we have already discussed, and you can browse the lectures to get into the understanding that what is the theory behind these topics. Over here, we are just going to discuss the examples, so we may also understand this thing that besides theory, we may also understand this thing that how to use the theorems and the estimation theory to solve the practical scenarios. So let's go with it. The first problem that we have in hand is you are supposed to be a director of a transportation safety, and you are concerned because the average highway speed of all the trucks may exceed the 60 miles per hour speed limit. A random sample of 120 trucks show a mean speed of 62 mph. Mph is for the miles per hour. Assuming that the population mean is 60 mph and the population standard deviation is 12.5 mph, we have to find the probability that the average speed is greater than or equals to 62 mph. Now, as there are always some keywords in a problem. When you are solving an examination or a problem or a question, always uh, try to explore the keywords present in the question, because many times it happens that the keywords basically help us to understand the concept which is running in the problem, and definitely to solve it as well. Like for example, over here, a very important keyword, like many keywords are over here in this problem. The more the keywords we have, the easier it becomes to solve it. Like over here we have a keyword which is a random sample of 120 trucks, and the mean of this sample is 62 mph, right? The population mean is 60 mph, and the population standard deviation is 12.5 mph. These are all the keywords which will definitely help us to solve the problem, or at least to identify the formula which could be used to solve this question. So let's start working on the solution. Firstly, we are provided with the sample information having a sample size of 120. The sample mean, which shows the speed of the trucks, is 62 mph, and sample mean is indicated by x bar as we have already discussed. So please be careful with these symbols. Population mean mu is equals to 60, and the population standard deviation is 12.5 miles per hour. We have used a subscript p over here to indicate that the standard deviation is of population, or you can simply write sigma as well, because sigma normally always indicate it's a population standard deviation symbol. Using this information, it is required to find the probability that the average speed is greater than or equals to 62 mph. So definitely this English language statement can be translated mathematically into something like this: that probability of x bar is greater than or equals to 62, and we have to find it, so it's a question mark. Since the probability or area is required, so we first need to definitely find the z values, and then by using the z table, we can find the required probability. So it's a simple thing to do. Now we have two z formulas, remember. The first z formula is used when we have the random variable as just the measured values, and it is told to us that these measured values follow normal distribution. That z formula is x bar minus mu upon sigma, which is where sigma is the standard deviation of the random variable. But the second z formula that is used uh, is, is applicable when the random variable is not just a normal random variable, but rather it's a special type of normal random variable because it contains all the sample means. So it's basically a sampling distribution of the mean. So since we are provided with the sample information, and rather we have to find some probability related to the sample mean. See the highlighted portion, the x bar greater than or equals to 62. So this indicates that we would be needing to convert this x bar into z value, and the formula to convert the x bar into z value is the formula which is shown over here, that x bar minus mu sigma p upon root n, right? So we have to be careful when we are using the z formula. So this z formula would be used over here. So using this information provided, it shows that we are given a sample mean, which must have been taken from sampling distribution of mean, and therefore we have to use following z formula to solve for z, and this is the z formula that we have to use. Now, if you like to graph the problem, so it's quite simple to do so. We have uh, we have basically a normal distribution, which is the normal distribution of the sampling distributions of the mean, and from from that normal distribution, we are provided with just one sample, which is x bar given to us, which is 62. So since 62 is a value which is greater than the population mean, and we know that in a normal distribution, the population mean comes in the center, and the central value of a sampling distribution of the mean is also a population distribution. So it's also a population mean that we verified in our previous lecture of central limit theorem. So the graph would go something like this: that this, although this is the graph of the sampling distribution of the mean, on the horizontal axis we have all the sample means, but the central value of the sample means would definitely be a population mean value, and this is 60 given to us. And since the given sample has a mean which is 62, which is greater than 60, so it should be lying ahead of it, on the right side of it. And the area that is required to us is basically shown by this arrowhead, which is the greater than 62 area, or greater than x bar given to us. So we have to find this area. So the first step is to convert the x bar into z, and using the formula and the calculations shown over here, we can see that how this x bar can be converted into z value, which is simple equation: x bar minus mu sigma p upon root n, that is 62 minus 60 upon 12.5 divided by root 120, because 120 was the sample size given to us. So it is easy to see that how the calculations are going. And when we do these calculations, we get a value which is 1.75. So basically this means this thing, that x bar has been converted to a z value which is 1.75. So the graph of the problem would come out something like this. This is the graph for a standard sampling distribution of the mean, where on the horizontal axis we have the standard z values. Central value mu is 0, as we all know that in a standard z table, or in a standard z calculation, the mu comes out to be having a 0 value. So the 0 value is in the center, and our z value is 1.75, which is a positive value. But definitely, since it is positive, so it should be on the right side of the 0. And the area that is required is again the same, that is greater than 1.75, which is equivalent to x bar 62, right? So remember this thing. Since we cannot directly find the greater than probabilities from the table given to us, therefore, this problem can be solved in this way: that probability of x bar greater than or equals to 62 is the same as probability of z greater than or equals to 1.75, which is basically the same as 1 minus probability of z less than or equals to 1.75. We know that the whole area of a normal distribution is equals to 1, or that shows the total sum of the probabilities, which is 100%. So in order to find this area, we have to basically find, we can do it in this way. The technique is this, that we just find the area which is lesser than 1.75, and subtract this area which is less than 1.75 from the area of the whole normal distribution, which is equals to 1. So that's how the technique goes. And looking into the z table, we get something like this, that 1.7 on the 1.7th row, on the positive part of the z table, on 1.7th row, and 0.05 column, because 1.7 plus 0.05 is 1.75, we will see the intersection which is coming on, and this is basically 0.9599. So that means that probability of z less than or equals to 1.75 is basically 0.9599. When we subtract this probability from 1, we get an answer which is 0.0401, which basically shows this thing, that there is 4.01% chance, or 4.01% of the time, a random sample of 120 trucks from the population will yield a mean speed of 62 mph or more. So it's 4.01% chance that we get a speed which is greater than 62 miles per hour. So that's how the solution goes. I hope this problem is understandable to everybody. Let's move on to the next problem. Now the next problem is basically related to the uniform distributions. So let's first have a brief review of what a uniform distribution is. A uniform distribution is a very important continuous distribution which is used in probability and statistics. It is a family of the distributions which are basically rectangular distributions, and it is also symmetric in nature. And the most the most important part of this distribution is this, that every value in this distribution has an equal probability. So whenever we have a case of equal probabilities, as we have in ungrouped data statistics, remember, so we always get a uniform distribution. This uniform distribution is defined basically by two parameters. The first one is called A and the second one is called B. These are the standard terms for it. The A is basically the first value of the distribution and the B is the last value of the distribution, where we get some probability or some value which is other than 0. These are also called the minimum and maximum values of the distribution. Well, we are only concerned with the means and the variance and the standard deviations. So rest of the things are just for our general discussion, like the PDF of it or the way we write it. It's just for our general discussion. The mean of the uniform distribution is given as the middle value of A and B, that is A plus B upon 2. And the variance of the distribution is given by 1 upon 12 B minus A whole square. Now we are not going into the derivation or detail of it, that from where these formulae came from. We would just be using them in our calculations. So keep remembering these formulae. Definitely, if it would be required to solve for a uniform distribution, you should be provided with these formulas so that you can use it. Now what the question is, let's go with the question. A study involving stress is done on a college campus among the students. In certain college campus, I mean, a survey sort of thing is being done about the calculation or the measurement of the stress. The stress scores follow a uniform distribution. Now it is known to us that stress follow a uniform distribution with the lowest stress score equal to 1 and the highest or the maximum equal to 5. Now we took a sample of 75 students from the college campus, and in that sample we have to find the probability that mean stress score of the sample of 75 students is less than 2 in part A, and in part B you have to find the 90th percentile for the mean stress score for a sample of 75 students. This basically means this thing, that at 90% area what would be the corresponding sample mean value. That's basically meant by it, because we have to find the mean stress score. So definitely we are talking about the sample mean over here. So please be careful with these keywords. The mean stress score basically means the sample mean. Okay, and over here in part A as well, you have to find the probability that mean stress score. So again, the mean term is a keyword over here, which will tell us that which Z formulation we have to basically use. Now we are provided with the sampling information with a sample size of n75. Using this information, it is required to find the probability that the average or mean stress score is less than or equals to 2. That is, probability of x bar is less than or equals to 2. We have to find this probability. Since probability or area is required, so we need to first calculate for the z value, and then by using the z table, we can find the required probability. Now when we are doing all these things, we must realize this thing. I am recalling you this thing, that we are assuming this thing, that the sample information given to us is part of a sampling distribution, right? And we know this thing by central limit theorem, that when we have all the samples in the sampling distribution, then they basically make a normal distribution, having the central value. The central value of that normal distribution would be the population mean, which is also the expected value of the sampling distribution. We have done all these verifications in our lecture of the central limit theorem. So I would again recommend you that if you have forgotten those things, then browse through those lectures, go through those lectures so that you can recall the things. So the Z formulation that would be used over here again is the same that we use for the sampling distributions of the mean. That is x bar minus mu upon SEM, the standard error of the mean, where again sigma p is for the population standard deviation and capital N is for the sample size. Many times students confuse into this thing. Always remember that capital N is for the sample size. Capital N is not for the population size. Okay, since it is known that stress scores follow a uniform distribution, that is as it is given in the question, so this basically means that the population is uniformly distributed. Furthermore, it is also mentioned in the question that lowest stress score is equal to 1 and highest is equals to 5. But I mean, please be careful in solving this question, because over here you are not provided concretely with the population mean and the population standard deviation. But you are provided with this information that it is uniformly distributed, having lowest and highest value these. So basically, it's indirectly you can calculate. I mean, indirectly, the question, the person is asking you the question is telling you that although you are not given the mu and sigma value, but you can use A and B to find the mu and sigma value. Because we have seen just now in the previous slides that the population mean, if it is belonging to a uniform distribution, is A plus B upon 2. That is sum of the minimum and maximum values divided by 2. And if you do this calculation over here, it's simple to do so. We get a value which is basically 3, which is 1 plus 5, 6 upon 2, which is 3. Likewise, as said earlier, we are not given with the population standard deviation. But since we know that it is a uniform distribution, so we can calculate the variance of this distribution using the formulation 1 upon 12 b minus a whole square. And if we plug in the values of b and a over here, we get a value which is 1.33. Taking square root of this 1.33 will give us the standard deviation, which will be definitely the population standard deviation, because we already know that the population is uniformly distributed. And this value comes out to be 1.154. So if we graph the distribution, if we graph the problem, we get something like this, that we have a normal distribution, and this normal distribution is basically the sampling distribution of the mean. From this sampling distribution of the mean, we are provided with just one sample, which is x bar is equals to 2. And now since we know that mu of the population is 3, that is a central value of this sampling distribution of mean is 3. So definitely 2 would be lying before 3, and it would go something like this as shown in the graph. And we have to find the probability of x bar less than or equals to 2. So we have to find the probability as shown, and I mean we have to find the area or the probability from the graph as shown by this arrowhead. So this is the required area. Now again the similar steps, we have to convert the x bar into z, right? And we have to use the formulation of the sampling distribution of the mean. And when we plug in the values of x bar, mu, and sigma p and n, we get a value which is minus 7.504. Now, since it's a negative value, it should be, because it is less than the population mean, so it's a negative value. Now, if we graph the same problem on the z distribution, we will get something like this. So, mu is equals to 0. Minus 7.54 is very far away from 0, so it should be very far away from 0. It should be shown something like over here. And we can see that the area which is less than minus 7.504 appears to be very, very, very low. And it should be. Although we cannot find this z minus 7.54 on the table, I mean, if you look onto the table to get the probability value corresponding to this z value, we will not get it, because the least value that is available to us on the table is minus 3.4, as you can see on your z tables. But from our z table, we can see that as the values go towards lower and lower values of z, the probability also goes towards very, very low value, assuming that it would be 0 as we go as far away from the population mean onto the left hand side or onto the negative side. As can be seen from the table over here, you can see that when minus 3.4 is a z value, that then this area or the probability is 0.0002. And as we move further away from the 0, that is, as we move further into the negative domain, negative region, then this probability would be reducing much lower. So we can assume this thing, that since 7.504 is very, very farther away from the 0 mean, therefore the probability could be taken as assumed to be or approximately equals to 0. So the answer to this question, part A of the problem, would be that the probability of the mean stress score to be less than 2 is 0, indicating that, I mean, if we say that 2 was a value which is quite near to 1, showing the low stress score values, so the chance of having this is quite low, very, very low. You can interpret this answer in this way. Now the part B of the question, for the 90th percentile, what we have to do is this: we take the one tailed area from the left hand side, and we would basically see onto the table that where we are getting a value which is 90% or close to 90%. By close to 90%, we mean that the area should be conformably covered. The z value used to give this area is as shown in the following graph. So you can see in this graph that where we get this value. So over here you can see we have a value which is 0.9015, and we also have a value which is less than 90%, which is 0.8997. Now if you remember from our previous lectures, we mentioned this thing that when we do not have exact probabilities on the table, then what we can do, either take the value which is lower than the required probability and a value which is higher than the required probability, and we also find the corresponding z values for them and take the average of it. Like one approach could be that we take a value which is 1.28 and the second z value which is 1.29, and then take the average of the two. But I personally prefer this thing, that uh, it's better to take that probability value which confirms that the area has been covered. So that's why I'm taking this 0.9015, because 90% was required and 0.9015 definitely covers this 90%. So corresponding to it, the z value is basically on this row which is 1.2, and on this column which is 0.09, and the sum of 1.2 and 0.09 makes it equals to 1.29. We will look for this probability. Remember, we look for this probability in the positive z column or in the positive z part of the table, because 90% is definitely greater than 50%, and every probability or area which is greater than 50% comes in the positive z portion, and every probability of area which is less than 50% would come in the negative z part of the z table. So keep remembering this thing. So the solution to this part B would go something like this, that for 90th percentile, the z value is z equals to 1.29 from our table, which we just got it. Hence, corresponding sample mean x bar, which is required actually, which we were actually required to tell this thing, to answer this thing, that what would be the corresponding x bar for the 90th percent area of the graph. Remember this thing, that we are on the sampling distribution of mean. So every point on the horizontal axis is a sample mean, right? So every area corresponds to a sample mean, and we are asked to give that sample mean which corresponds to 90% area. So we will use the C formulation that we use for the sampling distribution of the mean again over here, and for Z we would substitute 1.29. For x bar we will plug in the nothing, because we have to find the x bar value. So keep remembering this thing. But the population mean is 3 over here, and the population standard deviation which we just calculated is 1.154, and the sample size is 75. So rearranging the equation and doing the calculations, we get an x bar which is 3.17. So the answer could be put in this way. That's important, and to see how we are writing the answer. The 90th percentile of the sample mean of stress scores corresponding to a sample size 75 is about 3.17. This tells us that 90% of all the means of samples having a sample size of 75 are at most 3.17, and 10% are at least 3.17. It's simple thing to understand, because this is the x bar value which we have obtained, which is 3.17. So definitely, I mean, before 3.17, we have the area which is 90%, and after 3.17, we have an area which is remaining 10%. So it is basically at most at 90% and at least for the remaining 10%. I hope this is understandable, right? So that's how we basically put the answer. Now let's move on to the next problem. The next problem basically entails the information related to exponential distributions, and it's an interesting problem. Just like uniform distributions in probability and statistics and data analysis, we also have a very important distribution which is called an exponential distribution, or sometimes also called as negative exponential distribution. This distribution basically shows that how the PDF, or the probability density function, changes exponentially with time in such a way that it is declining. When it is declining, as you can see from the graph, when it is declining, then this is basically a negative exponential. But it may also happen that that this function increases with time. Then it becomes a rising exponential or a positive exponential distribution. Now, again over here, I mean, the rest of the details are just for our general information. The very important part about exponential and particularly negative exponential distributions is this, that the mean of the distribution and the standard deviation is same. So whatever the mean is also the standard deviation of the negative exponential distribution. And this is the information that we are going to use in the next question. So the question is this, that suppose that a market research analyst for a cell phone company conducts a study of their customers who have exceeded the time allowance included on their basic cell phone contract. The analyst finds that for those people who exceed the time included in their contract, the excess time follows an exponential distribution with a mean of 22 minutes. So what actually has happened so far in this question is this, that there's a market researcher or market research analyst who has been given the task by his project manager or by his heads to see or survey this thing, that how much, I mean, to have the survey of this information about the people who have basically exceeded their their cell phone contract time limits. And his study shows this thing, that the access time used by the customers follows basically an exponential distribution with a mean value of 22 minutes. It should be a negative exponential, because definitely there should be a time limit after which the cell phone company would stop giving them the required hours that they want to basically use for the communication. So it should stop somewhere. So it should be a negative exponential distribution. Now, furthermore, in the question, it is said that the market researcher took a random sample of 80 customers who had exceeded the time allowance included in their basic cell phone contract. Now, it is required to find the probability that the mean access time used by the 80 customers in the sample is longer than 20 minutes. You have to find this probability that the mean access time is greater than 20 minutes. You have to basically work on this probability. That what is the chance of occurrence that the mean access time has exceeded 20 minutes. Okay. In the part B of the question, we have to find the 95th percentile of the sample mean access time for the samples of 80 customers who have exceeded their basic cell phone contract. Now remember this thing, that in this question, the sample means indicate the means of the access time, right? So the physical quantity is the access time whose means have been taken, and definitely this would formulate a sampling distribution of the mean. And we are just provided one such sample from that sampling distribution of the mean. So in part B, we have to find that which sample mean corresponds to the 95% area of this sampling distribution of the mean. So let's move on to the solution of the equation. It follows a similar pattern that we have just discussed. Like we have the sample information with the sample size of 80, and we have to find the probability of x bar greater than or equals to 20. That is probability of the sample mean greater than or equals to 20. And remember that this is the sample means are the means of the access time. So you can also put it in this way, that probability of the average access time is greater than or equals to 20. You have to find a chance of occurrence of this. Again, since the probability is related to sample mean, so definitely we have to make use of the C formulation, which is used for the sampling distributions of the mean. So the first step would be to calculate the Z value using this formula that is given over here again, like the previous questions. And the second step would be to find the probability or the area related to this Z value. Okay, now over here, since it is an exponential distribution and the mean given from the for the distribution is 22 minutes, and we have just discussed this thing, that in an exponential distribution the mean and the standard deviation are same, particularly for a negative exponential distribution. So we are going to use this information to solve the problem. The graph of the problem can be made in this way, that we have sampling distribution of the mean, where on the horizontal axis we have sample mean values. The central value of this sampling distribution of the mean, which is also the population mean, is 22, and the sample given to us has a mean value which is 20. So definitely it will be on the left hand side of this population mean, and we have to find the area which is on the right hand side of this x bar value. We have to find all this area which is on the right hand side of the x bar 20 value. So the steps are again very simple. First, find the z value corresponding to x bar, and using this formula x bar minus mu upon SEM, we get a value which is minus 0.8131. It should be a negative value because it is a value for corresponding to an x bar which is less than the population mean. So once we have got this minus 0.8131, we can graph the problem as the z distribution, and it goes something like this, as you can see on the slides, where mu is 0, the central value, and z is minus 0.8131, and it is on the left hand side of mu 0 because it's a negative value. Since we cannot find directly again the greater than probabilities from the table given to us, the z table, therefore we would make an approach similar one. We have just used that probability of x bar greater than 20 is same as probability of z greater than minus 0.8131, and which is basically equals to 1 minus probability of z less than minus 0.8131. Because remember this thing, that we cannot find directly the probabilities of greater than regions. Rather, what we can do, we can find the lesser than region probability and subtract this answer from the whole area of the curve, which is basically 1. So this is the approach that we use for finding the probabilities or areas which are for the greater than regions. So looking onto the z table for minus 0.8131, we will get something like this, that this is over here we have minus zero point 0.8 as you can see from the red arrow, and zero point 0.01 on the column as you can see from the red arrow, and the intersection of this row with the column gives a value which is 0.2090, right? So this 0.2090 or 20.90% probability is for probability of z less than or equals to minus 0.8131. When we subtract this answer from 1, we get a value which is 0.791 or 79.1%. So the answer can be put in this way, that the probability is 79.1% that the mean access time is more than 20 minutes for a sample of 80 customers who have exceeded their contracted time allowance. One more thing, since this is, I'm not running the slideshow over here because many times I have to basically mark something on the slides or highlight something on the slides. But since this is quite a microscopic value, so for your understanding, I'm going to basically show the zoom of this slide, and I hope this works over here. Yes, it goes something like this. So you can see this is 0.2090, right? So that's how we can basically see that how this probability was obtained. Now, part B of the solution is similar one as it was for the previous question. You have to find a 95. You have to find that x bar or that sample mean which corresponds to 95% area of the distribution of the normal distribution, or of the normal distribution of the sampling distribution of the mean. So for 95th percentile, we take one-tailed area. We always do this using the one-tailed area that is from the left-hand side going towards the right-hand side. The z value used to give this area is as shown in the following graph and the z table. So this is, I think this is visible to us, so we don't need to make a slideshow for this particular slide. So we have 1.6. We have to solve it in this way, that we will locate the 95% probability on the positive z, because 95% should be on the positive z, it is greater than 50%. So we have to locate 95% on the positive z, and as since we do not get exact 0.9500, so I've picked up the probability which confirms that 95% area has been covered, which is 0.9505. So the row corresponding to this 0.9505 is 1.6 as shown by the red arrow, and the column corresponding to this 0.9505 is zero point 0.05 as shown by the red arrow. So 1.6 plus 0.05 is 1.65. So this is the required z value. Now since we have got the z value, which is 1.65, we will plug it in this equation to get the x bar. So 1.65 is equals to x bar minus 22 upon 22 divided by root 80, where mu and sigma, remember, they were 22. And when we do this calculation after a little rearrangement for x bar and doing the calculation, we get 26.058. So 26.058 is actually that sample mean which corresponds to 95% area of the sampling distribution of the mean. And in other words, you can also put it in this way, that all the area before 26.058 would be 95%, and all the area after 26.058 would be the remaining 5% of the distribution. So it's a same thing as putting it in this way, that this tells us that 95% of all means of the samples are at most means that we are at the maximum value, but there are lower values as well, are at most 26.058, and 5% are at least 26.058, because after 26.058 we have remaining 5%, and till 26.058 we have 95% of the distribution. So I hope this is understandable. Let's move on to the next question. And again, this is some sort of small in font, so I'm going to make a slideshow for this slide as well. So suppose scores on exams and statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of scores with sample size equal to 36 gives a sample mean of 68, and we have to find the confidence interval estimate for the population mean exam score for 95% CI. In part A and in part B, we have to do the similar calculation, but assuming that the 3 points is not the population standard deviation, rather it is a sample standard deviation. So this last problem is basically related to the estimation. We have to do the estimation. We have to estimate the population mean using the given data set. In part A, the data set is this, that we have a population standard deviation of 3, a sample mean of 68, and a sample size of 36. And in part B, we have all the things remaining, but remaining as they are, but just the population standard deviation has been replaced with sample standard deviation. So this gives, and we have to do all this calculation at 95% confidence interval. Remember, CI is for confidence interval. And remember this thing, that when we are provided with population standard deviation and we have to do the estimation, then we use the Z table or the Z distribution. But when we are given a sample standard deviation rather than the population one, then we have to use the T table. So in this problem, we'll also see that how we actually read a T table. So let's start working with the problem. This is an estimation problem, as we already discussed. Population mean is to be estimated. Fine. Since population standard deviation is known, hence we will use this formulation, that z is equals to x power minus mu upon sigma p root n. And if you do a little rearrangement, then mu equation comes out to be this, which is x power plus minus d sigma p root n. We substitute all the values over here. X bar is 68, sigma p is 3 and 36, and the z value. Now remember this thing, a very, very important point. Whenever we have an equation which shows some interval, like over here, the equation for the population mean mu is with plus minus sign, then this basically means that the distribution is being viewed from the central value. That is, we are going towards both the tails. So the z value would always correspond to the area taken from the central value. We have discussed this thing in our previous lectures, that how we basically calculate, how we look into these areas from with three different views, from the central view, from the left tail, or from the right tail. If you have any problems in understanding it, you can go back to the lecture slides and review this thing, that how we basically find the z values corresponding to three different areas that we can have on a normal distribution. So the z value is 1.96. Again, we determined this thing previously, that how this 1.96 is obtained. So no need to discuss it again. But if you want to have a view of it, so you can view back the slides in which we discuss this problem. Substituting all the above values in the estimation equation, we get mu is equals to 68 plus minus 1.96, 3 upon root 36. And after doing this calculation, we get mu is equals to 68 minus 0.98, and the second value of mu is 68 plus 0.98. Now the value of mu, which is basically 68 minus 0.98, is the lower limit estimate of the mu, and the value of mu, which is 68 plus 0.98, is the upper limit estimate of the mu. So we get two answers, 67.02 and 68.92, which can be interpreted in this way, that the interval estimate of the population mean mu at 95% confidence interval is 67.02, from 67.02 to 68.98. So what do we mean by this? We mean that in this interval, we are 95% confident that the population mean exists. Or to put it in this way, if 100 samples would have been taken, then 95 of them would show a population, would show a mean value within this interval, which is 67.02 to 68.98. So this is the interpretation of this interval estimate, or 95% confidence interval estimate for this particular problem. Now part B. Now again, since it's an estimation problem, so all of the points are the same, but only the equation changes. We have to now use a T equation rather than the Z equation. The difference between a T and a Z equation is this, that T uses the sample standard deviation and Z uses the population standard deviation. So we have all the things as they were. We just plug in the values in this equation for the estimate of mu, and we get again a lower estimate of mu and then upper estimate of the mu, which is 66.979 for the lower estimate and 69.021 as the upper estimate. So what do we understand is this, that at 95% confidence interval, the population mean would lie within this region, or within this interval, having a lower limit from 66.979 to an upper limit or an upper value of 69.021. Now over here, it's very important to see that how we found the T table, from the T table, the T value. Now let's look into this thing, that how a t table actually looks like and how we find the values for it. This is a short glimpse of the t table. The actual t table is over here, and I have taken a short glimpse of it so that we can focus on the problem. Now, please understand this thing very carefully. I want your full attention over here, your full concentration over here, that how we basically read a t table. Over a, on a t table you can see this thing. The first three rows are for the cumulative probabilities, one tail and two tail, and then we have df, which is an indication of degree of freedom, and all these are the degree of freedoms which are mentioned over here. Okay, and inside the t tables are the probability values. Sorry, not the probability values. Inside the t table are all the t values. Okay, so be careful with this thing, because in the z table, inside the z table we have all the probability values, but in the t table, inside the t table we do not have the probability values, we only have the t values. Okay, the probability values are mentioned over here in the rows which are two tails and one tail, but the probabilities are not easy to understand. We must know that how these probabilities have been written. So for example, if I'm working on 95% confidence interval, then instead of 0.95, I would find a probability which is the remaining part of the normal distribution or a t distribution after excluding 95%. So that becomes 0.05 or 5%. So this means, let's focus on the problem so that it becomes easy to understand. This means that since I'm working on a two-tail problem, because I'm looking into the area from the central value, so I'm working on the two-tail problem. So I would come onto the row which is two tails. Then on the two tails, I have I have a confidence interval of 95%, and that confidence interval of 95% is not indicated by 0.95 value, rather it is written by 0.05. So I have to locate that where on this row of two tails I'm getting 0.05, and over here there it is 0.05, which is also shown by the red arrow over on this table. I've marked it with a red arrow. Now remaining is the degree of freedom, DF. Remember this thing. In our lecture of sampling, population and sampling, we emphasized on the DF. And if you forgot the DF idea, then I would suggest you that go back onto the slides and see that what the DF is. Over there, we understood that the degree of freedom for this sample standard deviation is n minus one, capital N minus 1, that is the sample size minus 1. So the DF over here is basically N minus 1 values for the sample standard deviation, right? And in our case, the sample standard deviation was basically what? It was what value? Uh, So the sample standard deviation was 3 value, but the sample size was basically 36, right? So we had a sample size of 36. So this makes a degree of freedom which is 36 minus 1, that is 35. But the interesting thing is this, that we do not find any value 35 over here, right? So what we will be doing now, we would pick that value which is lesser than 35, that first value which is lesser than 35. Now on this t table, the first value which is lesser than 35 is 30. So we will pick the row containing this 30. If we were, if you would have been given directly a 35 value over here, then this would have been the best for us. But since 35 is not given, so we will pick that first value which is less than 35, and this is 30 over here. So the work is done now. We pick the row which is 30, we pick the column which is 0.05, and the intersection of it gives a value 2.042. So that's how we obtain the 2.042 t value, and that's why we put 2.042 over here. And so the calculations for mu went by that 2.042 multiplied by 3 by root 36, and then it was added and subtracted with 68. So that's how we basically concluded with the estimation of this part B using the t table or using the t distribution. I hope that it is understandable to everybody. The lecture that we did regarding these example problems, it was easy to understand, it was understandable to everybody. But and over here in the end, I have also shown the z tables again and the t tables again, because they are very handy. They are always used in the statistical inference problems. So still, if you get any problem, any query, any question, any confusion, as I always say, that I mean, learning is by question answering. So if you have any questions, you can write down on the comments, and I will try to get back to you as soon as I read them. Okay. Thank you very